We would like to welcome our speaker and partner, Steve Shapiro. Steve has been in the mission-critical industry for over 30 years and has a diverse background in the study, reporting, design, commissioning, development, and management of reliable electrical distribution, emergency power, lighting, and fire protection systems for high-tech environments. His experience also includes providing analysis of critical applications support facilities. Steve has an extensive experience in the design and management of corporate and mission-critical facility projects with over 4.5 million square feet of raised floor experience, over 200 megawatt of UPS experience, and over 350 megawatt of generator experience. Steve is the author of numerous technical and articles and seminars. Steve, we are excited to have you present our webinar on the future of the UPS systems and battery technologies. Thank you, Steve. Go ahead.
Thank you, David. This is going to be a fairly high-level review of battery technologies and how they have been changing over the years and how they impact your UPSs and your data centers. So for the agenda, we're going to review basic battery information, basic battery types. We're going to look at the old technologies. We're going to look at the newer technologies. We're going to look at how these batteries are affected by codes relative to what you can and can't do and what you can and do, what you must do in a room. We're going to look at a total cost of ownership analysis for various types of batteries. And then we're going to look at some of the UPS technologies and how they're impacted by these batteries. And then we're going to take some questions. So as David said, please put your questions down in the notes for the session, or we'll unmute everybody at the end to get some questions. So basic battery concepts. Everybody knows from high school what a battery looks like. You've got an anode, you've got a cathode, you have an electrode, and the ions are moving, or the electrons are moving from one to the other, causing a voltage to and a current to be made. We're going to talk about the big technologies that are out there, and then we'll talk a little bit about the newer technologies. So lead acid has been around forever. In fact, most of these technologies have been around in one form or another for a very long time. But lead acid has been used extensively in the flooded cells. As you can see, the big jelly jar that's in the upper left-hand corner. That is a typical technology that's been used forever for telephone companies and for UPS systems throughout the world. Then we've moved to valve-regulated lead-acid batteries, which look more and more like your car battery. In this configuration here, or in this configuration here, they come in an absorbed glass mat. They come in gel cells, and they also come in a pure lead or a lead tin thin plate type environment. And you'll see as we go through the analysis of all the different technologies, you'll see the pros and cons of each one of those. We'll talk a little bit about lithium-ion, we'll talk about salt-based batteries, and then we'll talk a very little bit about the new solid-state battery technologies. So flooded cell batteries. So typically people will say flooded cell battery is something like a jelly jar. It's a gigantic polycarbonate jar that has lead plates in it. And so what you can see on the right-hand side of the screen, each jelly jar is made up of cells. Sometimes the jelly jar can be one big cell. Sometimes it has multiple smaller cells in it. Typically each cell is good for about 2.2 volts. And that's based on an N cell voltage. So a fully operating battery is about 2.2 volts. When a battery is discharged, it could be at 1.67 or 1.65 or 1.63 volts per cell. And in a UPS system, you add up all those voltages, and that's how you get to your float voltage on your UPS system. So each of these cells is made up of a grid or lead grid or lead plate. And these plates are interchanged with as positive and negative plates with separators. And the positive plates are usually a lead oxide, with the negative being pure lead. And then there's an acid or a sulfuric acid that's used as the medium to transmit the electricity between the systems as the transfer material. So major modes of failure for a flooded plate. These grids, as you can see at the very bottom, there's little feet on the bottom of the grid, and as this grid sits in this jar, the grid tends to flake, and those flakes fall to the bottom. And so one of the modes of failure that you'll see is when these plates corrode and the material falls to the bottom, and you can get shorts that go from plate to plate. This material can potentially reduce the capacity of each of the cells in the battery. So loss of the active material due to this shedding, and then internal shorts when that material falls to the bottom. And over time, so the jelly jar cells or the flooded cells are typically a 20-year battery, or they're talked about as a 20-year battery. There are other configurations that can go longer, but typically the service life and the grid thickness are where you're going to see these things change. So as the service life goes up, the grid thickness tends to dissipate. Regulated batteries. So let's talk a little bit about gel cells. And so the gel is used to suspend the electrolyte. These are typically, you could find these gel cells, they look more like a car battery, as you can see in the lower right-hand corner of the screen. If you drop them on the floor, theoretically nothing leaks out, and we'll talk a little bit about that and the impact in your room later on. But they're supposed to be totally corrosion and maintenance free. Nothing ever is really totally maintenance free. No off-gassing, though there is some hydrogen that can be produced. So in the flooded cells, there is definitely hydrogen produced during charging. We have issues with authorities having jurisdiction, not necessarily understanding the difference between a flooded cell and a valve-regulated cell, and requiring hydrogen detection and hydrogen exhaust in a valve-regulated environment. One of the things that does typically happen with these jars is that they're placed very close together inside cabinets, and so they tend to get warm. And so in some cases, we've actually added ventilation to the cabinets to maintain the proper temperatures in the battery cabinets to keep the batteries as long as life as possible. Some of the disadvantages with these types of batteries are that as they age, the capacity fades, and that's true in any battery, but these tend to age faster. So these are available in a 5, 10, and even a 15-year environment. But when these fail, they typically fail violently. And when a flooded cell fails, it typically fails open. So you actually lose voltage. But in the case of a valve-regulated cell, especially these gel cells, they tend to fail violently. The absorbed glass mat is the same configuration, basically. No liquid electrolyte. You can get a deep cycle cell. They typically last longer, so you'll find these are more in the 10-year time frame. And when we say that it's a 10-year battery, we typically mean that it's a 10-year warranty life, but you typically have to change these in 5 to 7 years, whereas in a 5-year battery, you typically have to change them in 3 to 5 years. That flooded cell battery is a 20-year battery, and you typically need to change those in 14 to 16 years. And the reason they call them 10, 20, 15-year batteries is that there's a warranty on it, and that warranty is typically a degrading warranty. So in year 1, you get a full replacement, but in year 10, depending on the type of battery, you get some prorated value associated with those batteries. So in the absorbed glass mat, same type of disadvantages. The biggest issue really is that violent failure. Pure lead. So we're seeing a big move towards the pure lead environment. The technology that's available now gets you a slightly longer design life, but allows you to get a shorter time. So there's an effect called coup de grace, or it's a French term. It basically means that you can only go so short with these batteries, and then there's no time. So you can take a pure lead battery down to 5 minutes initially, and over time it will degrade to 3 to 2 minutes. The effect of going too short, or designing too short a time, means that you don't have any real degradation time. So if you designed a flooded cell battery for 5 minutes, you wouldn't get 5, 4, 3, 2, 1 minutes. You'd get like 2 or 3 minutes, and then it would just fall off. And so these valve regulated batteries in the thin plate environment allow you to design to a shorter discharge time. And so we're seeing more and more colo environments where the economics of the situation, you know that your generator needs to be up in 10 seconds or 15 seconds. So designing to 15 or 20 minutes of battery isn't necessarily their target, and they're looking for somewhere between 5 and 7 minutes or even a little shorter. And these pure lead thin plate batteries are a good alternative to that short time to make sure that you've got your coverage. So disadvantage is shorter discharge times than a typical valve regulated battery, but you're designing to that. But they're a little bit more expensive than the valve regulated battery because you're getting a little bit more of a warranty on them. They're a little bit longer life, and you're able to get that shorter discharge time. So in this chart, we're looking at the standard valve regulated lead calcium battery versus the pure lead battery, and we're looking at cycle life. And you can see that the pure lead battery, I hope everybody can see the pointer here, but the pure lead battery is built for a lot more cycles than your typical AGM valve regulated battery. So you can see as the cycle time, as you increase the cycles, the life drops off on the typical AGM valve regulated battery, but for the pure lead battery, if you're doing quite a few cycles, that cycle time doesn't kill the battery that quickly. And so it goes out to several more cycles. So one of the other benefits of the thin plate battery is that you can cycle it more. So we talked a little bit about the major modes of failure when we went over the different technologies, but ultimately the internal shorts, the thermal runaway, and the negative plate undercharge are other issues associated with valve regulated batteries. And here there's a little bit of a in-depth description of the different failure modes and how they're affected, and everybody can get a copy of these slides as well as get a look at the video, so I'm not going to get too deep into them, but mostly the loss of element compression is due to the contraction of the separator plates, and you tend to lose capacity when this happens. The internal shorts, we talked a little bit about that with the flooded cell batteries, but it happens with valve regulated as well, where you get plate growth and it goes through the separators and you end up shorting those plates out. Thermal runaway. So as these batteries get warmer during a discharge, it generates O2, which eventually turns into H2O, and there's less thermal mass to absorb the heat, and you can get higher and higher temperatures, and the thermal runaway is something that will destroy the batteries. That violent failure and potential fire can result. The negative plate undercharge really comes out of the way the battery charges and recombines with itself, and so you end up with an undercharged negative plate, and you can typically deal with that as long as you're aware of it, and we'll talk a little bit about battery monitoring towards the end of the session. As a battery degrades over time, you'll see that if you could take a battery apart in the middle of its life, you'd see that these plates tend to start to disintegrate or corrode. And so what you see on the left-hand side is a fully corroded plate, whereas on the right-hand side, it's almost a completely new plate. And so over time, these plates will dissolve and you lose capacity within your systems. Gas evolution. So as batteries charge, they tend to produce hydrogen, especially the flooded cells. So we monitor the room to make sure that we don't get a lot of hydrogen in the room, and if we do, we have exhaust fans to deal with it. But you'll find that more and more authorities having jurisdiction are requiring ventilation in valve-regulated rooms, as well as sometimes even direct ventilation of the battery cabinet itself. It's hard to explain why the interpretations vary from location to location. You try to educate the local authority as best you can, but ultimately you're stuck with whatever they decide you have to do. So keeping that in mind, there's always that chance that you may have to provide ventilation in a valve-regulated environment. and even hydrogen detection. So this is a little bit more on how those gases are evolved from the battery during recharge. We'll talk a little bit about lithium-ion now. So everybody has seen or heard about cell phone battery explosions, and we need to understand that the cell phone battery, a lithium-ion cell phone battery, is not the same thing as the batteries we would use in our UPS system. You have power cells and then you have energy cells. And we're dealing more with the energy cells in a UPS environment. And each one of these batteries has its own battery monitoring system built into it so that it regulates the battery in charging and discharging and doesn't allow it to exceed the design criteria, which eliminates the issue associated with, or it's supposed to eliminate the issue with these battery cells catching on fire. So keeping that in mind, we look at the different aspects of a lithium-ion battery and all the different issues associated with it. And this is really just a reference table that goes through the different life cycles. But you can see that in a short circuit, theoretically there's no explosion or fire. And if you crush it, or if you drive a nail through it, or if it has some sort of impact, there should be no leak, no fire, no explosion. But we know that in the event of thermal runaway, we have had lead-acid battery fires. In fact, there was one recently at an energy storage facility for a utility in Arizona. And they weren't able to necessarily pin it on exactly what happened, but they know they have a battery fire, and they weren't able to determine exactly why at this point. So in the scheme of things, lithium-ion means a lot of different things to a lot of different people. You have lithium-ion is the overall family of battery, but different manufacturers use different chemical configurations. And so you'll have lithium cobalt, you have lithium iron phosphate, manganese oxide, nickel manganese. Each manufacturer is using their own slightly different technology to get their battery to work. And with that in mind, each battery has its own issues with fire protection in their space. So keeping that in mind, if you're going to use lithium-ion batteries, you should be talking to the battery vendor to determine what's the best fire protection system to use for that particular battery technology. And at this point in the life of these batteries, there aren't many fire protection technologies that work to put these batteries out. In most cases, these batteries need to burn out. So you need to keep that in mind when you're designing your battery rooms. And we'll talk a little bit about that later as well. So some different performance criteria or requirements around lithium-ion versus a lead-acid battery. The specific energy is much denser, much higher in a lithium-ion configuration. They last longer. They are okay with battery charge-discharge cycles. So ideally, you don't want to hit your batteries, or you don't want to discharge your batteries unless you have to. So if you have poor power quality in your facility and you're hitting your batteries on a regular basis, lithium-ion is a better technology to use because it can withstand a number of cycles, whereas the lead-acid batteries don't like to see that many cycles in the overall scheme of things. And what you'll find as part of your warranty is that there'll be a battery cycle monitor that's applied by the vendor or required by the vendor to maintain your warranty. And if you hit your batteries too many times, it'll impact your overall warranty on the systems. So there are several, and I've only listed a few here, but there are several manufacturers for lithium-ion batteries. Some are newer to the industry than others. Some of these batteries are in a form factor that is more conducive to locating in a smaller UPS, let's say in a computer room rack, versus in a large central type UPS system. But each of these vendors are looking at how to apply their technology for central UPS systems, as the central UPS systems are more prevalent in the data center world. Some of the total cost of ownership issues associated with these different batteries we'll cover as we look at the different battery technologies, but just know that lithium-ion batteries theoretically have the lowest total cost of ownership. They last longer than other batteries. They have a higher density of power. They have a lower maintenance requirement. They're less temperature sensitive. Ideally, these are great batteries if you didn't have to worry about fire protection issues, as you can see in that bottom line item there. And when we talk about new technology, we're looking for something that's obviously got a high density, obviously something that doesn't have a lot of maintenance associated with it, and something that we can deal with that doesn't involve some sort of liquid. Some of these newer sodium-based batteries, there was an older sodium-based battery that GE put out, didn't have much of a market, but there's a newer sodium-based battery that's available, or becoming more and more available, that they're testing in larger and larger UPS systems. So no spill issues, no temperature issues for storage, no charging issues. You can do deep discharges with no problem. You can ship it. And what's one of the problems also with lithium-ion is that shipping it, you're effectively shipping hazardous material, and so shipping it becomes an issue. But with these sodium-based batteries, that's not an issue. And keeping in mind that there's newer and newer technologies, these solid-state batteries that we're seeing, which are ceramic-based and crystal-based, they're not necessarily ready for prime time, but there's a lot of talk about them. Most of these battery applications that we're seeing as new technologies, like I said, are only available for small UPS, 2, 3, 4, 5, 10 kW in a rack type environment. When you're trying to scale up to an overall large data center, they haven't really packaged these to handle the large power requirements. They're working on it, but they're not quite there yet. So we talked a little bit about battery monitoring, and each of the different types of battery technologies, you can apply battery monitoring. Battery monitoring is important for you to be aware of the health of your battery, especially during a discharge. You can easily see which batteries are going to necessarily cause you trouble later on. The lithium-ion battery has internal battery monitoring built into it to manage the battery, but you can also see what's going on with that battery by connecting your systems to those battery monitoring systems that are part of those individual cells. Ideally, we put in battery monitoring systems whenever we can afford to do that for the client. The problem is that you can put the battery monitoring in, but if nobody looks at the battery monitoring, then you never know if you have a problem. So it's really important, just like looking at your BMS system or your electrical monitoring system for power quality, that you look at your battery monitoring system. Even if you're not doing a discharge, you look at it on a regular interval to make sure that you're not having issues with your batteries, because you really never know that you're going to have a battery problem until you go to do the discharge on those batteries, and then it's too late. So it is really important to monitor the health of those batteries. So let's talk about code. So in the old days, when everybody used flooded cell batteries, everybody was concerned about dropping a battery and getting sulfuric acid all over. There are spill containment requirements. There are eye wash requirements. The hydrogen detection that I spoke about, and the ventilation requirement during for charge and discharge. There's certain PPE that you're required to have, and signage and terminal barriers. So on those flooded cells that we showed in the original picture, in the initial pictures in the slides, you saw that the tops of those batteries can be exposed or not. So terminal barriers are pretty important in the overall working with those batteries and performing regular maintenance on those batteries. Most recently, people have been talking about NFPA 855 and the standard for the installation of energy storage systems. That is it's a standard and it's not a code, but a lot of what's in 855 or to be in 855 is in the International Fire Code for 2018, and as more and more locations or states and towns adopt 2018 Fire Code, you're going to find that more and more are looking at how these batteries are applied. And when you look at lithium-ion batteries, part of their total cost of ownership is that they have a very small footprint. But some of the requirements around the new codes are that you separate these battery configurations in certain quantities. So I believe it's 250 kWh size increments of batteries are separated by 3 feet from each other and 3 feet from a wall. So the size of the battery room tends to get larger and larger. And when we're looking at lithium-ion batteries, because of the fire protection issues, we're looking at putting these in dedicated rooms with higher fire resistance than your typical room would be. So the total cost of ownership of the part of the total cost of ownership that looks at the footprint of these systems tends to not be such a benefit anymore for those lithium-ion batteries. And so keeping in mind that there are issues with fire protection, there's also maintenance issues that OSHA and environmental issues that EPA will get involved with when it comes to disposal of different kinds of batteries. We need to be aware of all that. And IEEE has chimed in a little bit on all the different types of battery technologies. These 450 and 1188 tend to deal with the flooded cell and valve regulated battery requirements associated with testing and commissioning. But there are more and more people that are looking at all these different types of battery technologies and what can be done to deal with those. Total cost of ownership. So total cost of ownership takes into account how much it costs to buy it, how much it costs to maintain it, how much it costs to install it, to repair it, the physical footprint, how much real estate it takes up. Everything from birth to death of this system is supposed to be reflected in the total cost of ownership. And as you look at these total cost of ownership issues, we take all that into account when we're trying to evaluate one system versus another. So in this particular example, we're comparing flooded batteries to valve-regulated batteries. And we're looking at a large UPS system, a large plant, the 15 megawatt UPS plant. We're looking at the 20-year life cycle of this system. We have obviously taken into account the cost of money and the backup time, and we're looking at 20-year valve-regulated batteries versus flooded cells versus 10-year valve-regulated batteries, different UPS configurations, a total of 50 strings of batteries. And when we look at all the different configurations, we have to realize that we don't buy them all at once all the time either. So in this particular configuration, we were putting in some of the UPS day 1, some of the UPS in year 7, and some of the UPS in year 12. And so you can see those loads are going up as you go through the time lapse of the overall scheme of this data center. More and more batteries, more and more power. And when you look at all these different technologies, you have to look at the failure rates and the footprints and the maintenance costs and the overall life cycle of each of them. And then, so there's the initial cost for the material, then there's the life cycle cost for the material. So we looked at maintenance over a 20-year lifespan. We looked at the space requirements for all these different technologies. And then we put them into a cash flow table from year 1 to year 20. And what we found was that the most cost-effective system in 20 years was not a flooded cell system, because you typically have to change that flooded cell system in year 15 or so. So you're now in a 20-year life cycle, you're replacing that whole system. But if you looked at a 20-year valve, and the same thing for 20-year valve regulated, but when you looked at a 10-year valve regulated, you had different costs associated with that. And if you look at the overall scheme of things, you'd find that each technology is good for a different application. And so the annual total cost for each of these batteries reflected in this table shows that the valve-regulated battery was more attractive in the 1st and 12th year. But if you looked at the full 20, you could probably move together with a combination of these types of batteries. So the ultimate design recommendation was to put in a valve-regulated battery for day 1, but after the first replacement of that battery was for replacement to a flooded cell battery to get you to the full 20 years. So you're looking at one battery change out in this particular TCO. And so you had to plan your facility for the full flooded cell complement, but day 1 you had a fairly empty room because you were putting in valve regulated batteries. So this I'd like to say that every total cost of ownership analysis can be tweaked depending on what you really want that outcome to look like. If we were looking at a 15-year outcome, we would have a different recommendation for batteries. If we were looking at a 10-year outcome, we would have a different recommendation for batteries. So you have to understand what is the specific business case for your firm, for your application, because as those business cases change, the recommendations on total cost of ownership for the battery will change. This is a web analysis of lithium-ion versus valve-regulated batteries that's provided by Schneider. You can go to their website, and they have a whole bunch of really nice tools that gives you a very high-level evaluation of different types of systems. And you can see that this particular analysis looked at a 10-year life cycle. When you look at a 10-year life cycle, lithium-ion batteries are the way to go versus lead-acid battery. The life cycle for that, they're showing you, is only $188,000 versus $309,000. But if you tweak that to a longer period, you get a different answer. So again, TCO is relative to how you're using it. We'll talk very quickly about UPS systems. UPS systems have changed over the last few years. They've gone from transformer-based systems to transformerless UPS systems. Some of these systems have had ground current issues that have now been addressed by the manufacturers, and you need to be aware of it. Most of these types of systems, whether they're double conversion or hybrid type environment, can be adapted for any battery type. Typically, you want to, if you're going to start with one type of battery, you'd stick with that battery throughout the life. Otherwise, you'll have to make changes to the battery cycles and battery float voltages. But if you're going to go from a lead-acid-based battery to a lithium-ion-based battery, there are other technology changes that have to happen within the UPS. And you need to make sure UPS vendor is aware that you're changing your battery type so that they can tell you if they're compatible going from one type of system to another. And then there's a whole line of UPS systems that don't use batteries, really. Rotary systems can use a flywheel type technology to carry you over until your generator starts, or they have actual rotary batteries, flywheel based systems that can carry you for 5, 10, 15, 20 seconds until your generator starts. All these different technologies are interchangeable depending on how much space you have and how much money you have, because these systems will vary in cost and application over time. So we're getting towards the close of the technical part of the presentation. We've talked about battery history, lead-acid battery history, as well as the new application of lithium-ion batteries, and some of the complications associated with applying these different technologies to different UPS systems. And anybody who's really interested in getting deeper into any of these topics, we can discuss them further offline, but we're going to open it right now to questions. So if you have any questions, if you could either type them into the text box, or David will unmute everybody and we'll look for answers. I'll look for questions and I'll try to provide some answers.
Thank you. Thank you, Steve. It's been a wonderful presentation. If you have questions, please feel free to write them down in the chat room. And later on, if we have some time, we can unmute the microphone to see if anyone wants to ask directly. So why don't we start with the first question, Steve? Do valve-regulated lead-acid batteries require spill containment or special ventilation?
So as I mentioned, these batteries typically do not have a liquid base like a flooded cell battery does, and so typically would not require spill containment or hydrogen detection or ventilation. But like I had mentioned, it's sometimes very complicated to educate the local authority having jurisdiction without causing issues. So sometimes it's easier to provide it when they ask for it, as opposed to trying to explain to them what is really required by code and how we can get around, or how we can make them understand that it's really not required because the situation doesn't apply. We end up a lot of times putting in that ventilation and putting in that spill containment on a cabinet basis for a battery plant. Is there another question? Yes.
In one of the slides, you spoke about the disadvantages of valve-regulated lead-acid batteries, gel cell. So one of the disadvantages that you pointed out was that it fails violently. What do you mean by fails violently?
Well, they explode. So they go into thermal runaway and they'll explode. And so some of the benefits of putting them inside a cabinet is most of the time it'll contain that initial failure mode, but that is the nature of that technology. The Arizona fire that was based on a lithium-ion technology, I don't believe that they have come up with exactly what happened in that configuration. I know that these were batteries that were inside of a container, and a container being an ISO container. So in New York City, Con Edison, the local utility, is using energy storage technology to offset some of the demand requirements. And the local officials haven't necessarily committed to the best means of doing this. So what they've required Con Ed to do is put these things in containers in the street, and sometimes they provide fire protection in a gaseous form. Sometimes they don't. But ultimately, gas doesn't. In most of the cases I have seen, in fact, all the cases I've seen, people document, gas does not knock down a lithium-ion fire. There are talks of misting systems being able to knock down that fire, but I haven't seen any test results for that. But they put these batteries outside the building because we don't want the building to burn down. And in the event that some of these things catch on fire, you're stuck waiting for the thing to burn itself out before you can do anything.
How is the BMS regulate lithium-ion batteries during this discharge?
So theoretically, it looks at the battery and determines what's the proper voltage and current that it should be, and if it goes into some sort of runaway, it will isolate that battery from the string. In most cases, it can do that by either isolating the battery in some technology applications, or it can trip the breaker for the string and isolate the whole string of batteries. It doesn't necessarily stop thermal runaway, but it's one way of trying to regulate lithium-ion in that environment.
Thank you. I believe you mentioned, recently mentioned about the Arizona fire. Can you confirm that that was on lithium-ion batteries? And also, can you tell us a little bit more about this event and how can this be prevented?
Well, so prevention is something that everybody's looking at. I don't necessarily know if I don't believe that they found the cause of that fire. I do understand in the last information I read about that fire that when they opened up the container, that's when the fireball came out. But we don't have any information, or I'm not aware of any information that actually tried to explain what caused the fire. Most probably, it could have been a battery monitoring system failure that caused one of these batteries to go into thermal runaway, and they're packed very close together, and one causes the other one to go into thermal runaway, catch on fire, and explode. And typically, that's how these things will ultimately fail. If the battery monitoring system isn't working the way it's supposed to, you're going to have an issue. And in a data center environment, we have redundancy built in and we have concurrent maintainability, but each of these batteries is only provided with one battery monitoring unit. And if that battery monitoring unit doesn't work the way it's supposed to, you could potentially have a hazard associated with each individual cell within an enclosure or within a battery string.
Can you confirm the charging time of the lithium-ion batteries you mentioned from the state of charge of 0% to 100% in half an hour to an hour?
So the different battery technologies, the different chemical breakdowns of these different batteries will have different charging times. I believe we noted an hour and a half or 90 minutes of recharge time. That'll vary from technology to technology. I think as a general note, we had put in there an hour and a half, but it will vary from technology to technology. It's a much faster recharge time than you'll see with a lead acid type environment. It takes a much longer time to charge a lead acid battery than it does a lithium-ion battery.
Can you comment on potential design impact from NFPA 855 on lithium-ion installations in the future?
So there are a lot of presentations on on 855 and what it could mean until it's adopted and people follow it and people adopt the International Fire Code, the 2018 Fire Code. We don't necessarily know what's going to happen. One of the requirements is that these battery systems get UL listed at a certain capacity, and if they're UL listed, you can use them. If you looked at a megawatt of battery, or I should say a megawatt UPS with 15 minutes of battery, you're somewhere in the neighborhood of 250 kilowatt hours, and so that is the UL listed requirement associated with that battery. And if in those UL listed configurations, you need to have separation from one plant to the next. So if you had 3 UPS systems in one room, you couldn't necessarily have those batteries back to back. You'd have to have a spacing between them. And so that impact, and if it's not UL listed, then it's a different application. And so there's a whole group of presentations that are available on 855 and their impact. I know there's a lot of talk about 855 in the NFPA chat rooms, and we haven't seen how it's ultimately going to fall out yet. One of the things that we are looking at relative to lithium-ion batteries and their application in a facility is putting them in a dedicated 3-hour fire rated room to minimize their impact on the overall scheme of the facility. We do the same thing when we're looking at large size fuel oil tanks inside the building. When we try to put day tanks in over a certain capacity, code says that they can't be in the building. Well, one of the ways to deal with that code item is to put it in a 3-hour rated room, and effectively it's a separate building within a building. And that's one of the ways that we can deal with a lithium-ion battery environment. It's not cost effective in the overall scheme of things because it takes a lot more space, and you're losing the ability to put the battery with the UPS in the same room. And you need dedicated air conditioning, and it's just not ideal right now. I think the more people get to understand and deal with lithium-ion, the better it'll get. But right now, there's too many questions around the application of it.
Thank you. The battery monitoring system identified 10 to 20% bad or weak batteries of the total number of batteries in a large UPS system. Do you advise to mix new with old batteries, especially for mid-age batteries?
So that's always an issue. Ultimately, it's not cost effective to replace the entire string of batteries when you have a couple of bad batteries. We've typically provided spare battery racks and cabinets when we do new installations, so that if we end up with in 3 or 4 years on a flooded cell battery, if we notice we have a bad battery, we have a spare to replace it that's of the same age. Not necessarily the same number of discharge cycles, but at least it's the same age and the same type of battery, and we can replace those. But once you get above, I would say probably 20%, once you know you've got 20% bad batteries, you're probably looking at a full replacement of the battery string.
Another question is, what are some of the mechanical design considerations to install 100 kilowatts lithium-ion UPS in an electrical room?
Well, so I talked a little bit about the fire protection requirements. I wouldn't necessarily put the lithium-ion batteries in with the UPS systems, but just like in any other environment where you're putting batteries in with UPS systems, you need to be aware of the temperature requirements for those batteries. Usually the UPS systems can tolerate a much warmer environment, whereas the batteries don't. Lithium-ion can run much warmer, but when you're looking at lead acid, you want to be in that 77-degree range to get the ultimate performance out of that battery package. So the mechanical implication is that most of the time you have to provide additional cooling over what you would do in the event that you just had a UPS system in the room, which would impact your energy cost, which would impact your POE overall.
Steve, another question is, what about the new nickel zinc batteries?
So there is a new nickel zinc battery, and it's supposed to have a different list of issues, well, I should say less issues associated with the application of that type of technology versus lithium-ion battery. There is at least one vendor out there that has been going to the shows and showing us that those batteries work. But again, the form factor and the application for a large GPS system is something that needs to be addressed by all these different manufacturers. David?
Thank
Is there any
you.
other questions?
Yes,
Or are we...
there's actually a two-part question. Let me see if I can read it. It's a long question, but a very, very interesting question. Are you familiar with ASHRAE 90.4 data center energy standard? And that's one question. And then I can go to the other question if you want.
Go ahead.
So
sure.
The second one for that question or that combo is ASHRAE 90.4 allows a trade-off between UPS system efficiency and mechanical cooling efficiency. So the efficiency of the holistic system is evaluated. Is there a battery tech that is favorable over another when mechanical cooling and ventilation considerations are taken into account?
Well, so if you really want to take into account the least energy requirement associated with the UPS technology or the battery technology, you'd look at a flywheel or some sort of rotary UPS system that doesn't necessarily require cooling at all. But when you look at the different battery technologies on their face, lithium-ion is less temperature dependent than valve-regulated or flooded cells are, or lead acid in general. So a lithium-ion battery would be more energy efficient because it will require less cooling versus a lead-acid based battery. And you need to look at, in reality, the cooling associated with the infrastructure of a data center facility doesn't move the PUE arrow too far one way or the other. It's ultimately the IT equipment and the cooling of the IT equipment and that process that has the major impact on the PUE. You could be talking, 0.001 relative to the total PUE when you look at the cooling of one battery technology versus another, or versus the electrical infrastructure overall. People are now putting a lot of this infrastructure outside, so transformers and distribution gear and systems are going outside, so that not having to cool this kind of equipment, it becomes less of an issue. Some of these systems are actually going into shipping containers, and then obviously you need dedicated cooling for the UPS and the batteries in that environment. But we're finding that the cooling technology overall for the overall data center is what's driving that PUE and not the electrical infrastructure associated with it. David?
Thank you, Steve. So we're running out of time, but I do appreciate all of the questions that you asked. I wanted to open the chat room, but the audio, but I noticed that great questions and a lot of questions came up. So I really appreciated all of your comments and questions. For those who we miss to answer your questions, we're gonna reply to them offline. And also, if you have some additional questions, you can see in the screen Steve information, so you can contact him at any time. You have his phone number and his email. Also, he's on LinkedIn and Twitter as well. So if we move to the next slide, this webinar has been recorded and it will be available next week in our video tab on our EYP website. Please don't forget to follow us on LinkedIn. We're always posting new content, events that we want to participate or that we are the speakers or hosts, as well as news and webinar sessions that we will be hosting in the near future. If you have any topic that you want us to cover, we're happy to do so. And we're always happy also to hear any feedback from you. Thank you again for attending this webinar session. And thank you, Steve, again. Great presentation and great answer to all of the questions.